Hi everybody, this is Mr. Pope from Wilmington Grammar School for Boys, and this is the fourth instalment for the fast track math stuff that I'm going to be doing on Google Classroom. And today we're going to be handling mechanics for the first time. And we're going to be looking at one-dimensional problems, and we typically call them, well, it's not that they're one dimension, but they're generally in the just in one dimension. But we're going to be looking at problems with constant acceleration. Okay, so what is mechanics? Well, mechanics is all about the movement and the behaviour of real life objects as they interact. So, you know, whether you're just a person walking along and you've got a little ball and you decide to throw it up into the air and it comes down again, then we could use mechanics to answer all kinds of questions about this kind of motion. For example, given an initial starting height h of the ball above the ground and an initial speed or velocity thrown up into the air, could we calculate the maximum height the ball reaches, and could we work out the time which the ball is in the air? You know, there's all kinds of things we could calculate. And that's pretty much what we're going to be dealing with in this session. There's a couple of things I want to cover off first. So when it comes to measuring things, measuring quantities, we're going to use some very simple units of measurement, namely the SI units. And just so that we're all clear, whenever we're talking about distances, generally we're talking about meters. When we're talking distances or displacements, and I'll talk about the difference between distance and displacement. If I'm talking about speeds or velocities, then I'm talking about meters per second, and I'm going to write that as meters and then s to the power of -1. You might also have seen m/s, meters per second, but essentially that's the same thing. And then finally, we're talking about time. Now, we're usually going to measure that in seconds. Now, you don't have to. I mean, essentially, if you're working with a problem that's dealing with kilometers or hours or miles per hour or thousands of miles per day, you know, or picoseconds or nanometers, it honestly doesn't matter as long as you're consistent throughout the whole problem. But pretty much for this session and moving forward, we're going to be working with the SI units, which are meters and seconds in this case. I mean, there are 7 SI units, but just these two are going to be the ones we're going to be talking about today. So, let's back it up a bit. Now, I've given away speed is meters per second. Now, if we say speed is distance, meters, over time in seconds, then what I'm saying is meters per second is the same as meters over seconds. And essentially, the units on this side match up with the units on this side. That has to work. If somebody tells you something like, oh, well, it's easy, speed is just the same as distance times by time, how can you tell that person's wrong? Well, speed is meters divided by is meters per second, and distance times time is meters times seconds, if I was to look at the dimensions. Well, clearly, unless s is 1, which well, seconds aren't 1, seconds are a variable, then this doesn't make sense. So we can look at the dimensions, and it's a very skipped over form of dimensional analysis, but it does actually become important later on, and we'll talk about it in more detail when it comes up. But at the moment, I just, no pun intended, just want to get the mechanics of this out of the way. So there's a couple of things. Now, speed is distance over time, and to be specific, the speed over a certain interval is the change in distance over the change in time. Now, we've done a bit of differentiation already, and we should know that this is dx by dt. dx by dt. Okay, because that statement is saying the change in x per the change in time. A measurable change in distance over a measurable change in time as you let that interval between the two measurements become infinitesimally small. So, what is dx by dt? What does that mean? Well, it means if I have a speed time graph, something like this, where this is in seconds and this is in meters per second. Whoops. Nope, wrong way. This means that if I have a distance time graph, no, wrong way round. I'll get it right one day. If I have a distance time graph where this is in seconds and this is in meters, m, then if I have a straight line like this, and that straight line has a gradient of 2, then I can tell straight away the speed is 2 meters per second. Okay, it's really easy. Let's take another case. Let's suppose I was at a fixed distance and I wasn't travelling at all. So as time increases, the distance isn't changing at all, it's flat. Well, this clearly has a gradient of 0, and that's because we're travelling at a speed of 0 meters per second. We're not travelling at all. But next, there's going to be something really weird. What happens? What do you think it means if I've got a line going downwards like that? Let's say it's doing something like that, where the gradient is -3. Well, what does it mean to have a speed of -3 meters per second? That's weird. So, generally speaking, to get around this, first of all, speed being -3 meters per second is a nonsense. And the reason for that is we've talked a little bit before about vectors and scalars. Now, we talked about this before in the geometry and vectors component, but a scalar only has a quantity, whereas a vector has a quantity and a direction or orientation. So let's say, well, we have speed, right? That is a scalar. That's just a quantity. How fast is something going? If you said to a police officer, well, I'm going -3 meters per second. 1, he'd probably look at you funny because they don't work in meters per second. And 2, you don't really have negative speeds. They'd probably say, oh, well, if you're going minus something miles per hour, that just means you're going in reverse. So you don't really have a negative speed. In actual fact, its counterpart is a velocity. And generally speaking, velocity is what the term we're going to be using from now on. And now distance, that's also fairly ambiguous as well. If you was to say you're 3 meters away from something, that's fine, but how would you be -3 meters away from something? well, that just doesn't make sense. What we're going to use is something called displacement. Okay, so that has a direction and a quantity. So let's give an example of what would happen. Let's say the origin, O, of my axis is there. So positive displacement x is that way. And let's say the particle I'm dealing with here. Now, if I'm this side of O, I have a positive displacement, whereas the displacement is going to decrease, and then on that side I'm going to have a negative displacement from O. So negative, 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 zero displacement because I'm on it, positive, more positive, more positive, more positive. Now let's take speed. If I'm travelling from left to right, that's going to be a positive velocity. Whereas if I'm travelling from right to left, that's going to be a negative velocity. Okay, so dealing with things as vectors is going to tidy all of this up and going to give some value meaning to what's going on in a problem. Okay, and it's really important that when you're dealing with questions, you're getting a good idea in your mind of what's actually going on. I'll give you an example. Let's say I go back to, I'm just a dude on the planet Earth, and I throw a beanbag up into the air. It reaches a high point and then falls down. It hits the floor. Okay, now a couple of things. I am throwing it from 1.5 meters above the floor. I'm quite a tall guy. I'm throwing it maybe just over shoulder height, and I'm going to throw it with an initial speed of u, or I should say velocity. So let's define some key things. U, we're going to call the initial velocity. V, we're going to call the final velocity. A is the acceleration in the system, and again, this acceleration we're going to treat as a vector as well, because that has magnitude and direction. That's really important. We're going to let S be displacement, i.e. the total distance away from an original point. And we're going to let T equals time. Now that's a scalar. There's no direction to time. It just is. It's a scalar. So let's think about it. If let's draw a picture. Let's suppose that it reaches a maximum height of 4 meters above the ground. Let's think about all the different possible configurations that's going on here. Well, what's happening when time is 0? Well, the initial speed u is u. There is no final velocity because we're taking an instantaneous snapshot, so we'll just leave it as that. The acceleration, well, if I'm defining upwards to be positive, then there must be a downwards gravitational force, which I'm going to call g. So the acceleration is minus g. Okay, and the acceleration due to gravity, g, is approximately 9.8 meters per second per second. Now it depends where on the Earth's surface you are. Some physicists go as detailed as 9.81, and some maths exams like the old Cambridge Pre-U will just say it's approximately 10 meters per second per second. It honestly doesn't matter. If you want it to be precise, just use the value of g, and then things tend to just work out in the end anyway. Right, what is the displacement S at this point in time? We've just thrown it. Well, let's initialize that and let's say it's 0. Okay, so this horizontal is 0. Okay, now what happens when S is 2.5 meters? And what does that mean? It means if the total height above the ground is 4 meters, 2.5 meters above where I threw it, we are now at the top. Well, what's going on? Well, the acceleration is still acting downwards. What's the velocity saying? Well, the velocity is instantaneously zero. It's paused ever so slightly in the air. It's gone from a positive speed, less positive, less positive, less positive, zero, and then it starts to get faster going down. We say instantaneously at rest. And then finally, T, well, let's just call that snapshot T1. We don't know what that T value is. And then finally, what would this look like if I'm now dealing with the position when it's hit the floor? Well, I know S is going to be minus 1.5, because if I defined upwards to be positive, then we are now 1.5 meters in the opposite direction to positive, below where we initially threw it. The acceleration is minus g still. The velocity we're at now, I have no idea what it is, but it's now v, it's a final velocity. And now t, let's call it capital T for total time. Okay, now being able to play snapshots in your head and imagine how objects would move just based on your real life experiences, whether you go to the park, kick balls, throw balls, do whatever, that is going to be the most important thing with this topic. And if this is a problem to you, then you need to go out to the park, obviously not now because it's the coronavirus, but when everything's better, you need to go out and play ball with some family members or some friends, and you need to just get out there and enjoy the world. So, I'm not going to leave you in suspense. Let's try and work out what this time is, how long the ball's been in the air. Okay, now to do this is the main meat and bones of it. These formula, they're called the SUVAT, or constant acceleration formula, and the reason they're called SUVAT is because we're going to use SUVAT. Okay, I put them in a bit of a funny order, and to be honest, it doesn't particularly matter. But there's various SUVAT equations that you can use. Okay, and to be honest, I don't remember all of them. I just remember maybe 3 or 4, and I rearrange most of them, and it works out in the end. So here's the ones that I would consider pretty useful. 1, V equals U plus AT. Next up, S equals UT plus a half of A times by T squared. And next up, V squared equals U squared plus 2AS. To be honest, I think they're the only ones you kind of need. I mean, you can rearrange the top one to get V minus U over A equals T, or V minus U over T equals A. You could make some clever substitution to show that the second one here becomes S equals VT minus a half AT squared, and so on and so on and so on. I honestly don't care. The fact is, if you can remember a couple of them, then you're golden, to be quite honest. So, let's think about this. Well, let's suppose I want to calculate it. So, let's get some concrete numbers in there. Instead of U, let's say I throw it up into the air with initial speed of 2 meters per second. I don't know, maybe I've got a wussy arm. So the initial speed is 2, so U is 2. Okay, now we can break this up into stages if you want to, or you can just do it in one go. So let's take two snapshots in time. Let's take the original beginning and let's take the end. So how would I solve this problem? How long has the ball been in the air? Well, let's write SUVAT and let's write down what we know. Okay, what will be the total displacement between the beginning and the end? Well, I've already got that. It's going to fall 1.5 meters. So 1.5 meters down, if up is positive, means the net displacement after the action is minus 1.5 meters. What is the initial speed u? Well, I've defined that to be 2 meters per second up in the air. What's the final velocity? Well, I don't know what that is. That's just going to be v. What's the acceleration? Well, it's constantly accelerating downwards, minus g. And what's the total time? Well, that's just going to be capital T. So I need to work out what T is. And what other things do I know? Well, I know what S is, I know what U is, and I know what A is. So which equation on the right-hand side of this little SUVAT box only has S, U, A, and T in it? And after a little inspection, it's this one. So what's going to happen? We've got S, which is minus 1.5, equals ut, which is 2 lots of t, plus a half a t squared. Well, that's going to be minus g, half of that over 2 t squared. And now we're going to try and make t the subject of this. So if we times everything by 2, we're going to get minus 3 equals 4t minus gt squared. If we get everything onto one side to get gt squared minus 4t minus 3 equals to 0. This is just a nice quadratic to solve. So you can either complete the square or quadratic formula. So t equals minus b, so that's going to be positive 4 plus or minus the square root of b squared, which is 16, minus 4 lots of a, which is g, times c, which is minus 3, all over 2 lots of a, which is 2g. So t is going to equal 4 plus or minus the square root of 16, minus times a minus, that's going to be plus 12g, all over 2g. And then, now we know a little bit about surds, this is going to be 4 plus or minus. Both of these things have a common factor of 4, so that's going to be 2 root 4 plus 3g. Why? Because I can write this out as root 4 times root 4 plus 3g, because 4 times 4 is 16, and 4 times 3g is 12. This is all going to be over 2g, so t is going to equal, divide everything by 2, 2 plus or minus the square root of 4 plus 3g over g. So now we've actually got two solutions. We've got t can equal 2 minus the square root of 4 plus 3g all over g, or it can equal 2 plus root 4 plus 3g over g. Okay, so the next question becomes, which answer is valid? Well, if you plug into a calculator or just think about it very carefully, do you agree that 2 equals the square root of 4? So the square root of 4 plus stuff must be bigger than 2. So clearly, this one is going to give a negative t value, and that negative t value means we've gone backwards in time from the initial timer, and that doesn't make sense. Well, it kind of does. It means you imagine the ball has come up from the ground and gone through your hand, and you start the timer at 0, but that's not what's gone on here. So the only answer that makes sense is 2 plus the square root of 4 plus 3g all over g. And if you're interested, that is going to be 2 plus the square root of 4 plus 3 lots of 9.8 all over 9.8. And that works that to be where's the square root button on here? That works out to be SD. That approximately works out to be 0.79 seconds to 2 decimal places. So it's not in the air very long. And that probably makes sense because I'm not particularly high off the ground. I've thrown it a bit wussily. It's barely been in the air for a second before it hits the ground. Okay. By the way, we can apply this to loads of other different problems. And to be honest, I'm just going to do this by exercises. The other thing I wanted to talk about, and I kind of mentioned it briefly, is distance time graphs and acceleration time graphs. I just want to go over a few points. And to be honest, this is so GCSE, you should know this stuff already. But essentially what's going on is if I've got a distance time graph, and I've got something like this maybe, I don't know, then the gradient of a distance time graph is the velocity at which we're going. Okay, that's really important. Similarly, if I've got now a velocity time graph, and this is going to be really important as well, then the gradient of a velocity time graph is actually the acceleration. And now, interestingly, the area underneath a velocity time graph is the displacement. Okay, being able to draw these things is going to be incredibly important. And to be honest, when we delve a little bit deeper into calculus, you'll see why this is actually the case. But essentially, when you're dealing with distance time graphs, the gradient is the velocity. And you can probably see that already, because velocity is the change in x over the change in time. So it's the gradient in terms of, well, if the x-axis is the x-axis, but now the y-axis. Oh, what I've done here. I've done this the wrong way around, you silly boy. This is time, this is distance, displacement. And same thing here. This is time, this is velocity. I always get that the wrong way around. And acceleration is just the change in velocity with respect to time. And the operator to deal with areas we're going to cover shortly as well. So probably just best to dive in and give it a whirl. So let's have a look at this question. A sprinter runs a race of 200 meters. Her total time for running the race is 25 seconds. Figure 2 is a sketch of the speed time graph for the motion of the sprinter. She starts from rest and then accelerates uniformly to a speed of 9 meters per second in 4 seconds. The speed of 9 meters per second is maintained for 16 seconds, and then she decelerates uniformly to a speed of u meters per second at the end of the race. Calculate the distance covered by the sprinter in the first 20 seconds. Okay. So first of all, can we see why this diagram represents what's going on? It says a sprinter runs a race of 200 meters. So apparently the area under this thing, this total area here, and I can't be bothered to shade it, is 200. Okay, that's important. Okay, she starts from rest. Yes, that is an initial speed of 0. and she accelerates uniformly, i.e. a constant gradient. It's not curving or anything like that, it's a straight line to a speed of 9 meters per second. There it is. In the first 4 seconds, there it is. The speed of 9 meters per second is maintained. There it is for 16 seconds. And hopefully you can see why it's 16 seconds, because it goes from 4 to 20, which is indeed 16. Okay, this is making good sense so far. And then she decelerates uniformly, so she slows down at a constant rate, so it's going to be a line going downwards to a speed of u. So this height should be u on the vertical axis. Calculate the distance covered by the sprinter in the first 20 seconds of the race. Okay, so the distance covered in the first 20 seconds of the race is what's the area of this trapezium. Okay, there's various ways you can do this. You can either break it up into a triangle and then a rectangle, or you can bang it out in one go and do the trapezium. I don't particularly care. The point is, this triangle is 4 by 9 and then halve it, so 4 times 9 and halved is 18 meters. And then 4 to 20 is 16. And then times by 9, 9 16s I believe are 144 meters. So the total distance covered is 18 plus 144, which I believe is 162 meters. Okay, easy peasy. Find the value of u. Well, in this case, it might actually be easier to use the trapezium formula, the area for a trapezium, to work out what u is. Why is that? Because essentially the area of this thing, must equal 200 take away 162, which is 38. Now, what is the area of trapezium? Well, it's the two parallel sides, which appear to be u plus 9, then halved, and then times by the perpendicular height, which is 5, and this equals the remainder of 38. Okay, so how are we going to solve this? Well, if we do 38 divided by 5, I believe that's going to be 7.6, and if I times that by 2, that's going to be 15.2. Yep, so u plus 9 equals 15.2. So if I minus 9 from both sides, it looks like u is 6.2 meters per second per second. Easy peasy. The deceleration of the sprinter in the last 5 seconds. Okay, well, the acceleration, we know that from the SUVAT equations up here. The acceleration is just the change in speed over time. So the change in speed, so it goes from, it's 6.2 minus the 9 over 5 seconds, right? Now we're looking for a negative answer, because if it was positive, that means, because acceleration is a vector, if acceleration was positive, it means it's speeding up. If it's negative, it means it's slowing down. So 6.2 minus 9, and then divide the answer by 5. You'll get an answer of minus 0.56 meters per second per second. So it's slowing down minus 0.56 meters per second per second. Okay, relatively straightforward. This was an old A-level question. You know, a lot of it is just reading it and figuring out what's going on. So let's crack on to the next one. Another past paper question. So a stone is thrown vertically upwards with a speed of 16 meters per second from a point h meters above the ground. The stone hits the ground 4 seconds later. Find the value of h. Okay, so let's draw it out. It's always good to have a sketch. Here's the ground. And let's say the stone is initially here, and this is h meters above the ground, and it's thrown vertically upwards, and it's going to fall straight back down again, and this vertical speed or velocity, sorry, is 16 meters per second. Okay, well let's write out S, U, V, A and T. Let's think about what's going on. If I define the upwards direction to be positive, then what is S? Well, the net displacement is going to be minus H, because if 0 is here, it goes up to a point, then goes back down. So that's 0 displacement. And then it falls H. So actually the net wastage as it falls H meters down. What's the initial speed? Well, it's 16 meters per second up. What's the final velocity? I don't know, so I'll just leave it as V. What is acceleration? Minus G. It's G working downwards. Now, the acceleration isn't always minus G. You know, if we I'll tell you what, let's just for the giggles, let's just reverse this. If I define the downwards direction to be positive, then the net displacement S is actually H. Now, but the initial velocity is now minus 16 because it's in the opposite direction of what we're defining to be positive. V is, I don't know, it's V. A is now positive G. And T, well, we're told it hits the ground 4 seconds later. So what SUVAT equation links S, U, A and T? Oh, shock horror. It's that old S equals UT plus a half AT squared again. So S is H, UT is minus 16 times 4, which is minus 64, plus a half of G, and half of 9.8 is 4.9, times by T squared, which is 16. So 16 times 4.9, and if I minus 64, I'll get the height must have been 14.4 meters. So that's my answer for part A. Part B, find the speed of the stone as it hits the ground. Okay, so now I want to get V involved. Can I think of an equation linking V and some other things? Well, V, U, A and T, if you remember before, V equals U plus AT. Well, I know what U is now. U is minus 16. A is 9.8, sorry. And T is 4. So V is minus 16 plus 9.8 times 4. So minus 16 plus 9.8 times 4. Apparently V is 23.2 meters per second. So it's hurtling down, hitting the ground at speed of 23.2 meters per second. So yeah, fairly straightforward. Next question. If you want to pause it and have a go at yourself, I mean, I should have paused the other questions now, but you should have realised that yeah, you can pause at any time. Anyway, a car is moving along a straight horizontal road at time t equals 0. The car passes a point A with speed 25 meters per second. Okay, the car moves with a constant speed of 25 meters per second until 10 seconds go. And then the car then decelerates uniformly, so at a constant rate for 8 seconds. At time t equals 18, the speed of the car is v meters per second. And this speed is maintained until the car reaches the point B at the time t equals 30. Now, to be honest, I read it and I went, yeah, okay, so it's just going from there to there, it's slowing up, speeding down. I wasn't actually paying attention, I'll be brutally honest with you. Because for me, I want to read the part A or the part B or the question and say, right, what is it I need to do? What's the strategy here? And part A is sketching the space below a speed time graph to show the motion of the car from A to B. Okay, let's do that then. So let my time be the vertical axis. No, you silly boy. I always do this. It's the speed is the vertical axis because that is the dependent thing. And the time along the bottom, and this is in seconds, and speed is meters per second. Okay, so let's just do it as we go. At t equals 0, the car passes the point A with speed 25. Okay, so we're going to have a little mark here at 25 meters per second, and the car moves at a constant speed until 10 seconds. So that means it's going to be flat, it's traveling at a constant speed until here at 10 seconds. The car then decelerates uniformly for 8 seconds. So 10 plus 8 is 18. So it's going to decelerate uniformly, which means it's sloping down like so. So that's at 10, that's at 8. Don't have to do the dashes, I'm just showing for effect. At time t equals 18, yep, we've got that. The speed of the car is v. So then that point there, that's going to have a height there, v. And this is maintained until the car reaches the point B at time t equals 30. So, okay, so let's carry on. Let's move on. So 30 is going to be over here, that's in seconds. And this is carried on until we reach 30, like that. Okay, yeah, my speed time graph seems fairly legit. It's going to look like that. Given that A to B, where was A? A was when we started off and B was over here. Don't have to put that in your diagram, I'm just doing that just to remind myself. So given that A to B is 526, okay, meters. So what does that mean? It means the area of this whole thing is 526 meters. So the area of this is 526. That's what that means. Okay. Find the value of V. Right, well, in actual fact, you know what? I'm just going to do the whole thing. No, I'm not. I'm going to slice it like this. And I'm going to set it as the rectangle, which is going to be, so the total, so A to B is 30 times V, which is the area of this rectangle here. And then the trapezium plus, it's going to be over 2, half of the two parallel sides, that's 10 plus 18, so it's 28, times by the perpendicular height, which is 25 minus V. Okay, 25 minus V is that width. Two parallel sides are 10 and 18. Hopefully you can see that. So what we're going to have here, 28 over 2 is 14. So 526 equals 30V there, but then I've got 14 minus V if I expand the brackets. So 14 minus V is minus 14V, and 30V minus 14V is 16V. And then 14 times 25, well, that's 7 times 50, which I believe is 350. So now, if I subtract 350 from both sides, if I add 150, that's going to be 176 equals 16V. And then, that's just 11. So V is 11 meters per second by inspection. So that wasn't too bad. And the deceleration of the car between t equals 10 and t equals 18. Okay, what's the deceleration? Well, acceleration is v minus u over t. So what's the final speed? The final speed was 11, that's what v is, minus the initial speed, which is 25, over the time gap, or 10 to 18 is 8. So 11 minus 25 is minus 14. Minus 14 over 8 is minus 7 over 4. So I believe that's minus 1.75 meters per second is the acceleration. Okay. And that's it. Was an A-level question. I can't remember where it's from. Might have been from last year's paper. Who knows? Not a clue. I picked these questions out earlier today. Yeah, so hopefully we'll finish quite early today. I mean, I could have bombarded you with a lot more mechanic stuff, but to be honest, I'm going to pad it out a little bit. I think the algebra and number, I need to beast out more, but the mechanics. Anyway, so last question, we'll call it a day. So a firework rocket starts from rest at ground level and moves vertically. In the first 3 seconds of its motion, the rocket rises 27 meters. And the rocket is modelled as a particle moving with a constant acceleration a. Okay, so now this is interesting because we're no longer throwing a ball and there's no more force added to the ball, it's under free fall. The acceleration would only be due to gravity, so that would be easy to calculate. But this time there's clearly you know, this is my bad drawing of a rocket, you know, and it's fizzing there. And the point is there's gravity acting downwards, but then there's also this thrust of the rocket pushing upwards. The net effect is it's accelerating upwards, so that thrust is overcoming gravity. And we're going to try and figure out by how much. So we're going to assume that there's constant thrust. Now that's not necessarily the case. Literally rocket science, we deal with, you know, how the output of the forces may be constant, but the mass changes. So we're going to use calculus later on. I promise we're going to do that stuff, but it's not likely to be a constant acceleration. But I don't know, let's suppose this is a fairly large rocket and it burns fuel so efficiently and slowly that, I don't know, for the first 3 seconds it's made a very little dent in the fuel, and so therefore the mass hasn't changed much, and then therefore the net forces are more or less constant in the first 3 seconds, so the acceleration is the same. It's constant. So anyway, let's write out what we know. Let's take upwards to be positive. Well, how far has the rocket gone? Well, it says the rocket rises 27 meters. What's the initial speed? We don't know. U. Do we know what the final speed is? Not really. V. Do we know what the acceleration is? That's the thing we're trying to find. A. Do we know what the time is? T. Yes, first 3 seconds. Okay, interesting. So a fire rocket starts from rest. Ah, there you go. That's the key. It starts from rest. So if we start the timer exactly the instant when the initial velocity is 0, and then it starts to go. And now we have S, U, A, and T, and we want to work out A. Oh dear. As I said, you only need to memorize a few. S equals ut plus a half at squared again. So if S is 27, if u is 0, then ut disappears. We've got a half of a, and then t squared, so that's 9 over 2 lots of a. If I times by 2, that's 54, and if I divide by 9, that's 6. So the acceleration is 9 meters per second per second. What did they say? 6 meters per second per second. The speed of the rocket 3 seconds after it's left the ground. Well, that's also quite easy because V equals U plus AT. I know what U is, that's 0. I know what A is now, that's 6. And I know what the time is, it's 3. So V is 6 times 3 plus 0, so that's 18 meters per second. And then C, after 3 seconds, the rocket burns out. So the motion of the rocket is now modelled as that of a particle moving freely under gravity. Find the height of the rocket above the ground 5 seconds after it's left the ground. Okay, so let's do another SUVAT thing. So S is S. I don't know how far it is above the ground. U, the initial speed was 0. Or is it? No, it's not. Because it's not the position. Let's say we're now starting our timer at the 3 second point, right? Because the system's changed. It's no longer accelerating upwards. It's now acting gravity. So let's say U is now this speed of 18 meters per second. Okay, and now the velocity, we don't know what it is, the final velocity. The acceleration is now minus g. It's now slowing down because g is acting downwards. And t, now if you think about it, if we're at 3 seconds and I want 5 seconds, then I want t to be 2 seconds now in the future. So now I want to find s, and I've got u, a, and t. Ah, there you go. So it's same again. S equals ut plus a half at squared. So s equals 18 times 2, which is 36, plus half a, so minus g over 2, times by t squared, which is 4. So 4 and 2 cancel, that's minus 2g. So s equals 36 minus 2 lots of 9.8, which is 19.6, I believe. So 36 minus 19.6. So that means the total displacement in those 2 seconds is 16.4 meters. But you have to remember it's already 27 meters above the ground. So we add 27 meters to that. So the total height above the ground is 16.4 plus 27, which is 43.4 meters. Okay, so a little bit of a problem solved there. You had to figure out what's going on. And I think as long as you're fairly consistent, logical, and you just draw a little diagram and have a good mental image what's going on, these questions are quite straightforward. Anyway guys, thanks very much. Toodaloo.